CSI ETABS to see how we can elaborate with a fixed-based model and a flexible-based model to be able to model a structure considering soil foundation structure interaction. So for that purpose, I start with ETABS, and as a new model, I use the settings like the matrix SI, and I just set all of these to the Europe cases, but we are not going to design anything today. So it doesn't matter what you choose here. The only one is the first one, which is matrix SI units you would use throughout the whole example. So here I go with steel deck just to be to create a regular model, and I just want to create an arbitrary model. In X direction, I will go with 4. In Y direction with 2. Each span like 4 meter. And for the stories, I will go with 2 stories, each story 3 meter height. So I press OK, and we will have a 2-story building in 3D model, as you see here in 2 screens. And to reduce it to a very simple 2D frame, there are different ways to do that, but today I'm doing like selecting all of these and deleting them in the second floor, and I'm coming down to the first floor. I'm selecting these and I'm deleting these. So I'm only stuck with elevation 1. You can see in the right hand side window, if I zoom out a little bit, this elevation 1 is remaining. In the left hand side window, I go to the elevation 1 to better see the elevation, and I can select these nodes, 4 nodes, and assign them to joint restraint, and select this one like a fixed end. I'm assuming this is a reinforced concrete frame structure. So I press OK. The bottom points are fixed as a fixed end of columns onto the foundation. So you can assume that the foundation top level is at the base here. And for the rest of the nodes here, I want them just to behave in the 2D frame. So I go to the joint restraint, and if you take a look at the global coordination system, I can press this one, which means all of them are free, but they should be free in X and Y and Z direction in translational deformations. But I close Y because Y is out of plane, and I close rotation about X and Z because they are out of plane as well. So the rest of nodes are free to move in the X and Z directions for translational deformation, and they are free to move in the rotational Y, which is in plane rotation for the nodes. So I press OK. With this one, I'm pretty sure that the structure is just deforming in the 2D frame, in the elevation 1 frame plane, and there is no deflection out of plane or rotation out of plane. So now we go to define some sections for our columns and beams. And for that purpose, first of all, I go to the define menu, material properties. I already have C30, 37, the grade of concrete. I'm happy to take this as it is. This is the grade C30 of the concrete, but you can modify it or add any other material you want. And then I will go to the section property, frame section, and I will add a new property like from rectangular concrete I'm happy with. So I will take, I will name it like my theme, and I will go with 400 and 400. The material is C3037, as I said before, and I press OK. And I will add a copy of this property, and I will name it like my column, which is 40 by 40 centimeter again. And I will press OK. You can have different sections for your beam and column, but I will stick with these. So I will select these 6 beams and I assign frame property like my beam, press OK, and I select my columns, which are 8 frames selected here as we see, and I assign frame section property my column. So I press OK. So now I have all of the elements 40 by 40 centimeter, and then I will go to define my load cases. Like I have dead load and live load here. And for load pattern, I have dead load and live load. And the self weight goes to the dead load. So I'm assuming some arbitrary values for the dead load and live load. So I select my beams and I assign frame load distributed. For the dead load, I will put a uniform dead load of 50 kilonewton over the length of the beam over meter, and I will apply. And for the live load, I will go with something like 10 kilonewton over meter, and I will apply. For I need to reselect the beams. So assign distributed on live load 10, press OK. So if you right click on any of the beams here in the loads tab, you will see there is a 50 kilonewton over meter and 10 kilonewton over meter respectively for the dead and live load cases. So if you want to be more precise, you need to go to your detailing for the slabs in terms of dead load and live load. Go to the Eurocode to see what kind of live load you will get for your case example. Today, the focus is on how to model the soil structure interaction, and that's why we are going with arbitrary values for the section properties or the load cases here. So again, I go to define and mass sources. This is my mass sources, and I will go with dead load and live load, like a fraction of live load, 20%. This means that whatever I would get in the dead load and 20% of the live load will be transferred to define the mass matrix for the whole structure. And okay, so the lateral masses, long mass per story. Huh? Okay. I untick this one because the self mass is already in the dead load. So I'm happy with specified load patterns here. So I just save my model in some folder, wherever you're happy. Just make the structure interaction fill and the structure interaction model. Just save it before I want to try to run it. So now I'm ready to run this model, and it will take just a few seconds. because this model is not very sophisticated. And what I'm going to do is to take a look at the eigenvalues or natural frequencies of the model to see more particularly the first mode of the structure, and then compare it to the case of soil structure interaction. For example, this is the first mode of the structure, which has a period of 0.34 seconds. So this period is based on the fixed based model, as you see, which means the bottom of your columns are fixed. However, we know that we can go with a flexible sort of simulation of the frame with the foundation, with the underneath soil, which is a more realistic sort of modeling for the structure. And that's why I make a save as here from my model to just to name it flexible based model. And for that purpose, I start to model the foundation as well as the soil underneath the foundation. For that purpose, I need to release these points. And for that purpose, I assign them to the joint restraint. If my model was 3D, I would release them like three in every direction. But for this case, again, this is a 2D frame, so should be able to move in X and Z and rotation along Y, and the others should be closed because it's a kind of behavior in the 2D model. So that's why I do this for the bottom joints. And you cannot run your model now because basically this model is unstable statically because there is no support for this model. And yeah, if you run this model, you will certainly encounter sort of serious warning or error in your model because your model is not stable. So I go to define my foundation property, and for that purpose, I'm making a copy of this one, my foundation, and I try to use an arbitrary value of 2 meter lengths and like 500 millimeter depth, which means half a meter depth, like a strip foundation underneath the columns. So then you can change this if you want to see how the influence of the foundation stiffness is on your global behavior of the model. So I start to create some sort of frame element which has the property of my foundation, and from here to here to here and here. So you can see these three are representative of the foundation model, and still we need the underneath soil to be distributed underneath this foundation. And for that purpose, you need to go most specifically to the ASCE 41. Uh, this standard provides the uh, Winkler equivalent Winkler elements, which represent the soil underneath the foundation. If you go to table 8.2, and you will find some formulas like this, which gives you the equivalent stiffness for the springs you will model to be presented to be representative of the soil in the it provides you with six independent soil spring characteristics, and for each spring you will have a constant K value here, which is the spring constant value, the stiffness. You will have 6 different K values. And if your foundation is embedded, has embedments in underneath the soil, like the height of H underneath the soil, you will have some correction factors like betas. But anyway, you need to use these formulas to come up with the spring constants to your ETABS model. And for that purpose, I'm selecting these 3 elements, which are the foundations, and I want to assign the frames to the um, line springs. I want a sort of distributed line springs for these frames, and I'm modifying it. Okay, this is my springs, and you can have spring here like um, uh, you have local 1 direction, local 2 direction, local 3 direction, and rotation. So usually the local 1 direction is along the element, along the foundation element. Uh, so this is in terms of kilonewton over meter. The last over meter, it means it's distributed along the length of the frame element, the foundation element. And today I'm going to go with an arbitrary value of 10 powered by 7 for all of these spring constants, but you can use other values to see how it will affect your analysis results. If your analysis will be linear, only these parameters will be used. However, you can use these springs in a sort of nonlinear behavior, which is it's not really material nonlinearity. It's about the geometric nonlinearity because the soil can only tolerate the compression, not the tension. You can use only compression for the nonlinear analysis, which is more realistic in terms of soil foundation structure interaction. But as far as I'm doing linear analysis, these doesn't get into the game, and they will be activated only if you use sort of nonlinear analysis. So I will press OK, and I will press OK. You will see that you will have my springs underneath these elements. So should be somewhere here. Uh, my spring. See, you have a spring underneath your elements, and I can now start analyzing my structure, and I want to see how different the first mode of the structure would be in terms of uh, this soil foundation structure interaction. And if the spring constant is too high, it means that it's very stiff and it's like fixed space. But if you play with the spring constants, you will see it will influence your results. So if I go to the mode shape number 1, you will see that the first mode is 0.34, almost the same as you had in terms of fixed space. It means that the constant value for the springs I've used here is too much, which means that it's a very, very stiff sort of spring. And if it's very stiff, it means that it's equivalent to the fixed space. But if you unlock your model to be able to change, and if you go to the define and spring property, line spring, my springs is here. If you decrease the stiffness constant, of course, you need to calculate these values based on the ASCE, but I want to just give you the impression that this stiffness constant values for the springs have a major contribution to the soil foundation structure interaction. If they are very stiff, it means that your model is basically very close to fixed base model. However, if they are not very stiff, you have a certain level of soil foundation structure interaction into the game. That's why I reduced the stiffness by 100. I deleted two zeros from from those numbers. And if I take a look at the mode shapes here, you will have you will see the mode shape is 0.48 seconds, a significant change in the first mode of the structure. However, this is a simple model, and the modal shape doesn't have have not changed. But uh, let's see at the take a look at the modal shape. But maybe you can see the modal shape here. Just in a sec. This is the first mode of the structure, and as you can see, uh, the bottom of your columns are moving. It's not like they're fixed on the ground. Mostly for the first and last columns, they are rocking sort of motion. So this is the soil foundation structure interaction, and that's why for this kind of movement, the first period of the structure has increased. It means that this model, which is a flexible based model, has a sort of less stiffness than the fixed base model and a more flexible kind of modeling. So mostly in when today we are not going to the design phases, but when you go to design phases, because the soil foundation structure uh, model has a more flexible kind of stiffness and higher natural period, usually, not always, usually it's in the conservative side if you consider the fixed base assumption model to design your structure. However, this is not always the case, and mostly for some specific structure or some sort of uh, specific redundancy you have in the structure, this can be opposite, and the soil foundation structure interaction brings you to the area that the a sort of higher level of design would be needed. However, usually we use fixed base assumption, but we know that the flexible based assumption is more realistic and more clearly modeling the actual situation when a structure is connected to the foundation and sitting on the underneath soil. So with the flexible kind of modeling, we are trying to simulate a more realistic way the structure is behaving in real world. So the structure is sitting on the foundation, which are the bottom frames we talked about, and the bottom frames are sitting on some equivalent Winkler springs, which are representing the underneath soil. If the structure is 3D, okay, the springs would be sort of distributed on the area rather than in line. Anyway, in any case, you can calculate the stiffness for those springs based on these formulas, which you can see you have the total stiffness value. And if your model is 3D, you need to calculate its stiffness value and divide it by the area of your foundation, and you will find the stiffness value per square meter, for example. So, however, today I just divided I calculated some sort of that formula and divided by the length of the foundation because I was working in 2D frame system. So this is how you model the soil foundation structure interaction. You can obviously play with the spring forces with the characteristics of the foundation and the characteristics of the superstructure to see how influence each parameter has on the total behavior of the full structure. So, for example, if you add some shear walls instead of or along with the frame you have, you will see more effects of the soil foundation structure interaction. Basically, the more stiffer structure you will have, the more influence of the soil foundation structure interaction you will see if you model the whole structure with the soil foundation structure interaction. That's for today, and I hope you have grasped the idea of how we work with two different cases in terms of fixed based and flexible based modeling of the structure. Thank you very much for your